Wow, go on, my GCSE science students. Welcome back to another video. Now, in today's video, we're going to be going through chapter 3, structure and bonding. Okay, good. So, for this chapter, there are lots of topics. And the first one that we want to look into is atoms into ions, ionic bonding, giant ionic structures, covalent bonding, structure of simple molecules, giant covalent structures, fullerenes and graphene, and bonding in metals. And then for your triple science students, you need to look at nanoparticles and applications of nanoparticles. Okay, so this is a complete chapter review video, okay, for AQA. All right, let's go, because we have to get through this as quick as possible. So firstly, we need to know what's ionic bonding. Okay, so ionic bonding by definition, okay, ionic bonding is really the electrostatic force of attraction between a positive ion and a negative ion. Okay, that's what's called an ionic bonding. Now, you can see my previous videos as to how ions are formed, but let's look at an example. So, if you look at your periodic table, you will see that sodium, you're going to see that sodium is 11, 23. Okay, atomic number is 11, which means it has 11 electrons. Therefore, that's going to give us 281. Okay, and chlorine, if you look at your periodic table, you see that chlorine, it is 17 and 35.5. So it has 17 electrons. So that gives us 287. So sodium is not stable because it doesn't have a full outer shell. Now, what sodium will do? It will need to donate one of its electrons or gain 7. Now, the easier thing for sodium to do is to donate one of its electrons. So we're going to draw that using an arrow. Okay, and chlorine, which is also not stable because it has 7 electrons on the outer shell, would need to gain an electron. So you have the donation of the electron from the sodium to the chlorine. So ionic bonding must involve a metal and a non-metal. Okay, so metals are found to the left of the periodic table, left of the staircase. Non-metals are found to the right of the staircase. Okay, good. Now, after it's donated its electrons, we must then draw the after with a square bracket. So because sodium has given up one of its electron, it now has one less electron than it has protons, and therefore it has a positive 1 charge. And then chlorine now becomes the chloride ion with a square bracket around it, now has a minus charge. Okay, so these positive and negative, they attract each other, and that is what we call the electrostatic force of attraction. So that's the electrostatic force there. Okay, good. However, this takes a very long time to draw all of these shells. Okay, so we can use just the outer shell only. So that would be my sodium with 1 electron on it, and this could be my chlorine, which now has 7 electrons. We're using dots, we're using crosses. Okay, good. And this is now easier to draw, and then we just donate our electrons. Now we're going to try a couple of examples on the next couple of slides. So what you would have here is sodium, which is a plus charge, and then you would also have chlorine, which is a minus 1 charge. Okay, so here is the dot gained by the chloride ion. So you end up with now what's called sodium chloride, and because I've used 1 sodium, 1 chlorine, the formula is NaCl. Okay, good. So, all right, here's another one that we can try. Okay, let's try magnesium, which has an atomic number of 12. So if you go to your periodic table, you'll see magnesium 12 and 24, and sulfur is going to be 16 and 32. Okay, so now we're just going to use the outer shell only. So magnesium, that's going to be 282. So we're only going to put 2 electrons on the outer shell there. And sulfur is going to have 6 electrons on its outer shell. Okay, so that's going to be 286. Now sulfur, not stable. You're going to gain 2 electrons, so 1 arrow taken across one, another arrow taken across the other one. So magnesium now has a 2 plus charge because it's giving away 2 electrons which are negative, and sulfur now has a 2 minus charge. Oops, using the wrong one there. Okay, good. So let's get back our pen there. All right, so we have crosses, crosses, and now you're gonna have your 2 dots. Okay, so because I've now used 1 magnesium and 1 sulfur, my formula is going to be MgS, magnesium sulfide. Okay, now let's look at another example. Potassium, which is, if you look at your periodic table, you see that it is 19 and 39. So remember and then the sulfur now is going to be 32 and 16. So the 19 is going to give us that this is going to be 2881, and this is going to give us 286. So using the outer shell only, let's do our potassium. Okay, so that's my outer shell only. And sulfur, we know that sulfur has 6 electrons on the outer shell. Now, potassium is not stable. It has donated its electron to sulfur. Okay, so potassium is now stable. I'm going to put a tick there to show that it's stable. But sulfur is not stable. So sulfur then says to potassium, do you not have any other brethren there, or any other friend, any other mate that would like to donate its electron? And potassium said, yes, I actually know a next potassium atom out there who also wants to lose its electron, because sulfur is saying I'm still not stable. Here comes that potassium donating its electrons to the sulfur there. So now what you have used 2 potassiums, each having a positive charge, and we've used 1 sulfur accepting those 2 electrons from the potassium. Okay, here are the 2 electrons. Now, here we go. You now have used 2 potassium, so lowercase 2, S, and that is going to be the formula K2S. The formula is K2S, and the name is potassium sulfide. Okay, too easy. Let's move on to our next one. Let's look at lithium. Okay, lithium, which it is 3. So lithium is going to be, if you look at your periodic table, that's going to be 3, 7, and nitrogen, if you look at your periodic table, okay, this should actually be 7. Okay, so nitrogen is going to be 7 and 14. Okay, so using that, that's going to be 2, 1. Nitrogen is going to be 2, 5. So here are the 5 electrons on the outer shell. Good, that's your nitrogen, and here's your lithium. So lithium needs to lose 1 as it is not stable, so it's going to donate its electron. So that lithium is stable. However, nitrogen is not stable, so nitrogen says, don't you have any other lithium mates out there that would like to donate its electron to me? Lithium says, yes, I have 2 other friends out there who also have 1 electron on their outer shell. Donating its electron, donating its electron. So what you end up with are 3 lithium, each having a positive charge, and a nitrogen now having a 3 minus charge because it has gained 3 electrons. So here are the 3 electrons now being gained by the nitrogen. So the formula is Li3N, lithium nitride. Okay, and this is where formula writing is coming from. Okay, now what you need to appreciate about ionic bonding, you remember that we said that they have a positive and you have negative charges. However, it doesn't only form 3 lithium with 1 nitrogen, it forms a structure which looks like this. Okay, you have a repeating unit of positive and negative ions, okay, held together by these strong electrostatic forces. Okay, so it forms what is called a lattice structure. So this structure here is called a lattice structure. So ionic bonding gives rise to a lattice structure, and what is meant by lattice is just that it has a regular ordered structure of repeating units. So here you have negative, positive, negative, positive, positive, negative. It just keeps on repeating. And remember that there's a force between the positive and the negative, okay? And they then form lattices and crystals when they're solid. And actually, when you look in the textbook, they will refer to it as giant ionic lattice structures, okay? Good. So ionic compounds, they have certain properties, and most of these properties can be explained using this keyword or keywords here, the strong electrostatic forces, okay? So ionic compounds, they're hard because of the strong electrostatic forces, okay? Now, commonly asked question in your paper is, why do they have high melting and boiling points? So remember, and this is just an example of sodium chloride showing the positive and the negative. Remember that they form giant lattices, ionic lattices. They're held together by these really strong forces. And if something is held together by strong forces, it's going to require a lot of energy to break those forces, okay? And this goes for any ionic substance. So in the exam, they won't say ionic substance per se, but they'll give you, for example, they would say magnesium oxide. You just need to know that that's a metal bonded with a non-metal, okay? And because of that, you're going to know that it's ionic, and because it's ionic, therefore it's going to be a giant lattice, and therefore you can use those 3 points to explain why ionic compounds have high melting and high boiling points, okay? Good. Next up, ionic compounds are also well known for dissolving in water. And the reason that they're well known for dissolving in water is because water will break up their lattices into ions, okay? So you can see the lattice here, and in water, when it dissolves in water, it breaks up into its cations and anions, okay? Good. So ionic compounds, they only conduct electricity when molten or when dissolved in water, but never ever when they're solid, okay? Why is that so? Now, when they're solid, have a look at the structure here. When they're solid, there are no free ions. The ions are held together by those strong electrostatic forces. Now, what will happen is, because there are no mobile ions, they cannot conduct electricity, okay? However, when you melt them or when you dissolve in water, this term aqueous means that it is dissolved in water. Okay, let's just put H2O there. When dissolved in water, notice now that the ions are now free, and they're free to move around, and therefore they can conduct, okay? So to summarize what we've been saying so far, ionic bonding, electrons are transferred from the metals to the non-metals. You then form ions, okay? And very important to remember, it's between metals and non-metals, and then you form those ions, the positive and the negative charges. With ionic structures, the ionic bonding then gives rise to form giant ionic lattices. They have high melting points, again because of those strong electrostatic force of attraction. They're hard, they're brittle, which means that they break easily, and they conduct electricity when they're molten or they're dissolved in a solution. Now we're going to be looking at the next type of bonding. All right, so you've heard of ionic bonding. Now we're going to look at covalent bonding. Now, covalent bonding, let's have a look at this. We have two chlorine atoms here, okay? And you should know that chlorine is 287 because chlorine has 17 electrons. You know that from the periodic table, okay? So because they're 287, they don't have full outer shells, okay? But since they both don't have full outer shells, they decide that they're going to share, okay? Let's share those electrons, so 287 and 287. Why not come together and share? Okay, so now they can both think of those electrons as theirs. Okay, so in a sense, they're now both stable. And this is called a covalent bond. So a covalent bond is when you have a shared pair of electrons. So let's add that in, a shared pair of electrons. Okay, and we can represent this as Cl with a line. Good, and that line is just showing this shared pair of electrons. That line is just showing that shared pair of electrons. So that's a structural diagram, okay? Good. All right. So we've mentioned the line there. All right, good. Let's move on. Right. So now what we're going to do, we're going to just look at all the examples in the spec that they ask us that you need to know. Okay. So when you think of oxygen, we're just using the outer shell only. So it's going to be 2, 6. So we're now going to have 6 on its outer shell. Okay. Good. So 2, 4. 6 on its outer shell. Now what they decide to do, they both require 2, so now they're going to add 2 each to the bond. So now you're going to have, 2, 4, 6, 8. That oxygen is good, and you're going to now have 2, 4 left back. Okay, so look, we started off with 6 crosses. You must end with 6 crosses. They will count. Okay, and we started off with 6 dots. You must end with 6 dots. However, because you're sharing, it means therefore that each oxygen can refer to the shared electrons as their own, and therefore they're stable. And if we're drawing the shorthand structure, it's going to be a O with 2 lines bonded to another O. Why 2 lines? Because you're sharing 4 electrons, 2 pairs. Each line represents a pair of electrons. Okay, let's look at this example between oxygen and hydrogen. So using your periodic table, you should know that hydrogen is 1. Oxygen, it is 8, so it's going to be 2, 6. So that's going to be 1, and that's going to be 2, 6. So those are my dots for my hydrogen, and my oxygen, 2, 4, 6. So oxygen is not stable. Okay, it needs 2 more electrons. Hydrogen only needs 1 more. They're not donating, they are sharing. So hydrogen adds 1, because remember, the first shell only needs 2. Okay, good. So that hydrogen is okay. Oxygen shares 1. That hydrogen is now okay. Now we've shared 2, which means that the remainder has to be 4. And this structure, you all know it as H2O, which is a covalent structure, okay? And this happens with non-metals only. Don't know if I said that earlier, but this happens with non-metals only. Let's look at another example, okay? Good. So now we're looking at an example with nitrogen, which is, if you look at your periodic table, nitrogen is 7, 14, therefore the electronic configuration is 2, 5. Hydrogen is 1, and feel free to pause the video and try them, and then you check your answers after. Okay, good. So 1 for each of the hydrogen. Then your nitrogen, 2, 4, 5. Nitrogen needs 3 more. Hydrogen only needs 1, so that hydrogen is fine. That hydrogen is fine. That hydrogen is fine. So I've used 3, and therefore I should only have 2 X's left back for my nitrogen. They will check those, and this would be the structure here. Okay, good. And the formula is NH3, which you guys would know or should know, that is ammonia. Again, non-metals only. All right, good. Here is another one. Okay, you can take a picture, you can try that one as well. Okay, so we all has established that hydrogen is 1, carbon would have 4 on its outer shell, so 2.4. Okay, so what will happen, that was the structure would look like there. And again, CH4, and this now is called methane. Okay, good. And the final one that we will do, this one could be a little bit tricky for some students. So we have established that carbon, it is 2.4. Oxygen, we should know that oxygen, it is 2.6. Another oxygen, which is going to be 2.6. So this oxygen, let's put that in. 6 on the outer shell, so that oxygen requires 2. Okay, there are my 4 electrons there. That means that that requires 4. So let's look at what happened. For oxygen to be stable, it needs to share 2 electrons with carbon. Okay, so carbon puts 2 in, oxygen puts 2 in, therefore oxygen is going to have 4 left back. Again, oxygen is going to put 2 in, carbon is going to put 2 in, therefore we're going to have 4 left back, and none left back for the carbon, because carbon only started off with 4 on its outer shell, and the structure would look like this. Remember, each line represents a pair, so if I have 2 lines, that represents 2 pairs, 4 electron, and you guys know this as carbon dioxide. Okay, good. So I've done some common examples that could be asked on the paper. So if you have a sample of carbon dioxide gas, within that sample, let's say that is my container of carbon dioxide gas. In that sample, you're going to have millions of particles. Okay, between the carbon dioxide molecules that you have there, so let's circle them. These are called molecules, which you've just seen there. So each of those is called molecules. Between the molecules, there's a force. Let's use a different color for the force. Between the molecule, there is a force or forces. That force, you need to know that this force is called an intermolecular force. And unlike electrostatic, intermolecular force, they tend to be weak. Okay, intermolecular force, they tend to be weak. And if you are going to boil or melt or change the state, this is the force that you need to be thinking about. Okay, the intermolecular force. All right, so here are your weak intermolecular force that I spoke about just now between the molecules. All right. Now, what's the significance of the intermolecular force? Now, it is between the neighboring molecules, and as the molecules get bigger, the force gets bigger, and this also impacts the properties of some of covalent structures. Okay, so because they're weak, it means that they're easily overcome. It doesn't require a lot of energies, and this means that they have low melting and boiling points. Okay. So we're looking at the simple covalent molecules, and when we talk about simple covalent molecules, we're talking about all of those that we just drew. Okay, all of those are simple molecules. We looked at Cl2, F2, O2, H2. All of those are simple molecules. Now the intermolecular forces are weak, which means that it requires little energy to break them, and this results in low melting point. This also results in the fact that they are mainly gases or liquids at room temperature. Okay, good, and that's for simple molecules. So covalent bonding can give rise to simple molecules. Also, covalent bonding can give rise to a type of structure called polymers. Okay, now polymers are large molecules made from smaller units, building blocks, which are called monomers. Okay, good, and the monomers, they are attached via covalent bonds. Okay, so the monomers, their bonds break and then become joined up to make longer molecules. Here's an example. So we have ethene, double bond breaks, and several of this happen thousands of times, and now it becomes longer. So ethene here, you can see that the formula it is C2H4, and then polyethene, it can happen many times, 1 2 3 4 5 6 7 8 9 10 11. Okay, this can happen thousands of times. This is only a part of the compound. However, you will learn more about this in paper 2. Okay, you can have a look at my paper 2 content. All right, so that it is C11H22. All right, and these are covalent bonds. Okay, so covalent bonding, how I want you to think about this is that covalent bonding forms 2 types of structure. It forms simple covalent and it also forms giant covalent. Okay, so it forms simple covalent and it also forms giant covalent structures. All right, too easy. So when we talk about giant covalent structures, we're not talking about the carbon dioxide or all of those that we spoke about. All right, we know we're talking about some big structures, macromolecules of carbon and silicon. All right, so giant covalent structures, they have quite the opposite properties when compared to simple molecules. They're very hard, they're very strong, they have high melting and boiling point, they tend to be insoluble in water, and in particular, diamond is one of the strongest or hardest substance known to man. Okay, so here are two giant covalent structures. You need to be able to identify them. So that one there is diamond, and the next one, which is found in layers, that is graphite. You just need to know them. Okay, now when we're talking about the structure and bonding of diamond, here are the key points that you need to know. It is held together by covalent bonds. Each atom is bonded to four other atom. Okay, good. So it has the maximum number of bonds that it is able to form. So if you think about carbon, as we mentioned before, carbon is going to be 2 4. So all of those 4 electrons have been used for bonding, and because of this, it gives it certain properties. Okay, let's look at the properties. First up, it is very hard. Now, why it is hard? Make sure you can use this to explain. So because 4 covalent bonds per atom, it has a maximum number of bonds. Many of these bonds are strong, and therefore diamond is hard. Okay, too easy. Make sure you take that down. Next up, diamond does not conduct electricity. Why is this so? Because again, 4 covalent bonds per atom, all of the electrons are being used in the covalent bonds, therefore there are no free electrons to move around the structure, therefore diamond cannot conduct electricity. Okay, so those are the two main points that you need to know about diamond. Okay, now have a look at this. So we said that this before, it is graphite, which is a 3D structure which has the layers. But if you think about this one layer, we can take that one layer and get something called graphene, okay, which is a type of nanoparticles, which the triple science are going to look at later. Okay, so graphene only has one layer of carbon. So let's look at graphite structure and bonding. Now, key points, right? It's hexagonal. Okay, so it has a 3D lattice, and each atom has 3 covalent bonds, which therefore means that one electron is free. It also has weak intermolecular force between the layers. So here, between the layers, it has weak intermolecular force between that layers. Now, how does this affect its structure? Properties rather. So let's look at property number 1, excellent conductor of electricity. Now you should see this coming because you have 3 bonds per atom. It means therefore one of the electron is free to move. We call that spare electron. The word that they use in the textbook is that it's delocalized. It just means that it is free to move. And because it's free to move, it means that graphite can conduct electricity. Property number 2, it's soft. It can be used as a lubricant. Why is this so? Because you have the weak intermolecular force between the layers of graphene. Okay, good. Therefore, the layers, the forces between the layers are easily broken. And therefore, these layers, they can slide over each other. Okay, and because they can slide, means therefore that graphite can be used as a lubricant and it is soft. Okay, good. So to summarize, covalent structures, you have 2 types. You have simple, you have giant. When we talk about simple, we're talking about structures such as these. They tend to be liquids and gases at room temperature with weak intermolecular force, which are easily broken, which ensures that they have low melting and boiling points. Key points that you need to know. But for giant covalent structures, okay, we're talking about the allotropes of carbon, your diamond, your graphite, okay, and here are the properties. Make sure that you have that taken down. Now, another type of giant structure that we need to look at is fullerene. Now, fullerene looks like almost like a football here. It's a pentagonal and hexagonal arrangement of carbon atoms as shown there. Okay, now the atoms, they form a carbon sphere, and we refer to that as buckyballs, okay? Good. They are large, but they're not necessarily considered giant structures per se. And fullerenes, they're named because of their co-joined hexagonal shape carbon rings, okay? And then you have Buckminster fullerene, which is another type of fullerene made from 60 carbon, okay? C60, in which each carbon is bonded with 3 other carbon atoms. So therefore, you're going to have that free electrons, all right? Good. Lots of different uses for fullerenes, okay? They can be used as catalysts. They can be used to deliver drugs or medicinal drugs inside the body, okay? Good, and because they have a high surface area to volume ratio. Now, graphene, which is one layer of graphite, is only 1 atom thick, okay? It was recently discovered in the UK actually, and graphene can be rolled up into something called carbon nanotubes, okay? It is very, very strong and very flexible, stronger than steel actually, 100 times stronger than steel, and very, very flexible, and it is a very good conductor of heat and electricity because of those delocalized electrons free to move throughout the structure, okay? And it's almost transparent, all right? You almost can't see it, and it's actually used in a couple of phones, like those phones that are able to bend, all right? Very, very strong. Now, when you wrap that, it can then form carbon nanotubes, okay? Good. They're very thin cylinders, and their length is much greater than their diameter, okay? They have very useful properties because of how strong they are. They can be used to make tennis rackets. They can be used for reinforcing composite materials, and excellent uses because of their high electrical and thermal conductivity, okay? So we mentioned fullerenes earlier. We mentioned about their uses, delivering drugs, their lubricants. They can catalyze reactions, and they can use to make carbon nanotube, and very good for making electronic displays such as phones and computers. Okay, good. Now, metallic bonding. So we've looked at covalent, we looked at ionic. Now we need to look at metallic bonding. Now, metals are found in group 1, 2, and 3. Which means that they have 1, 2, 3 electrons on their outer shell. Now, in order for them to be stable, they just need to lose their electrons. Okay, so these are the electrons lost. Now, these electrons which are lost, they're free to move throughout the structure. So this is what metallic bonding looks like at the microscopic level. Okay, so the key points that you need to know about metallic bonding: they will form giant structure called giant metallic lattice structure. Why is it a lattice? Again, because you have that orderly repeating unit. Okay, the outer electrons, they are easily moved, and those outer electrons, they form a sea of mobile electrons. Okay, and there is a strong electrostatic force of attraction between the cation, so between the positive ions, and that negative sea of electrons. So those red dots are electrons. Let's use another color here, so you can see that those are the electrons which are moving out. All right, so the electrons are almost like a flexible glue which holds that structure together. And why is it electrostatic? Because it's between the positive and the negative. Okay, now you must be able to link bonding structures to their properties. Okay, good. So let's look at one. The outer electrons are delocalized, which means therefore they are good conductors of electricity. Okay, so what you see in the red is the structure, and then in the blue that is the property. Also, they have high melting and boiling point. And why is that so? Because of the strong electrostatic force between the ions and the sea of electrons. And they can slide, they're bendable, they're malleable, because the ions can slide over each other. Okay, now because metals are so soft and malleable, they can be strengthened into something called an alloy. Now, how an alloy works is, if you think about something which is pure metal, all of these would be your cations, which are layers which are easy to slide over each other because the atoms, they have same size. However, in an alloy where you have a mixture of atoms, if you notice that it disrupts the layers here, and therefore it is not easy to slide over each other. All right, so you can see the points there. Good. So those are alloys. Those are why alloys are stronger than metals. Key points. Too easy. Make sure you get that down. Okay. Good. Now, nanoparticles, this part is only for the triple. So if you're doing combined science, thank you for watching. This part is only for the triple science. Now, nanoparticles, all right, they are roughly, they're very, very small in size. So they're 1 × 10⁻⁹ meters in terms of size, okay? And when you think of nanoparticles, you just need to think about like something like a sheet of graphene that you saw earlier, okay? Good. Now, because of this, they have high reactivity because they have a high surface area to volume ratio, okay? And because of this, nanoparticles can be used for absorbing UV radiation, so therefore it is used in sunscreen and things like those because they're quite effective at absorbing the sun's ultraviolet rays. They're good for acting as catalysts. Catalysts are substances which speeds up reaction. They're good for cleaning glass, and they're quite good for allowing allowing the absorption of certain substance in the body. Okay, good. So they can also be used for delivering medicinal drugs using nano cages. All right, for fighting cancer. Good. And electronics, okay, because they're small and they're powerful and they're good conductors of electricity. However, what are some issues associated with nanoparticles? They can catalyze certain reactions, okay? They can have an effect on reactions that we don't want them to. Also, because they're so easily absorbed into the body, they might interfere with certain chemical reactions which is going on, okay? And some nanostructures are similar in terms of shape and sizes of certain chemicals inside the body, okay? Now, thank you for watching this video. Make sure that you like, share, and subscribe, and all the best in your GCSEs. I'm out.